College London. He's going to be talking about fun with floats, symbolic execution, floating point programs.
Can you all hear me at the back? Yes, no? Up, down? Oh, up. Awesome, great, thanks. Cool. Hi, I'm Liew from Imperial College London, and today I'm going to present symbolic execution of floating point programs. If you're not quite sure what that means, don't worry, I'll cover the background, so hopefully by the end you'll know what it means. This is joint work with Christian Kadar and Alistair Donaldson from Imperial College London, and also Daniel Schnell and Raphael Zal and Klaus Bow from RWTH Aachen. So, as I said, I'm going to give some background now on what these things are. So our previous speaker actually covered a lot of what some of the problems of IEEE 754, but I'm going to go over some particular parts of it. Then I'm going to give an example of some of the unintuitive behavior that can result from the standard, and then I'm going to explain what symbolic execution is and how it can help. So IEEE 754 is the floating point standard that basically says what the binary representation should be and how arithmetic should be performed. It sort of defines like 5 different classes of number. So this diagram tries to sort of illustrate what those are. So imagine this is the real number line. You have a special value that means minus infinity, plus infinity. You have in the middle how you have 0, but you actually have 2 different sorts of 0. So you have a positive and a negative 0, so you have a discontinuity here. You have these things called subnormal numbers, which are very, very close to 0. And then everything else in between is either a positive normal number, negative normal number, or positive normal number. The subnormals basically just exist to give sort of a smoother round off towards 0. So as you approach 0, instead of abruptly jumping straight to 0, it just lets you round off towards 0 in a slightly smoother way. For the normal and subnormal numbers, this is basically how a floating point number is represented. So it consists of 3 numbers. One is the sign, so this is an integer, it's either 0 or 1. It basically says is it positive, is it negative. You have the significand, this variable m here, which is a real number. And then you have the exponent here, e, which is an integer. So for example, you can write minus 12 as minus 1 to the 1 times 1.5 times 2 to the 3. Does that sort of make sense to everyone? Cool. So the standard has multiple different floating point types. So for example, binary 32 is, say, float in C, and binary 64 is double. It has a set precision, so this says it has, for the significand, you have 24 bits to represent that. And you have this other number called Emax, which basically tells you what the exponent range is. So for binary 32, that's between minus 126 and 127. So that's just a tiny bit of the standard. The standard is quite big. So onto some unintuitive behavior. So here's a simple C program. We've got some float variables up here, x, y, and z. This is assumed here, you can just read that as saying from this point onwards, just assume that this condition here holds. So that I'm saying here that x here, we don't know what it is, but it's not nan, and it's greater than 0. So it's a positive floating point number. Then after that, we set the sign 1 times 10 to the 12 to y, and then we do this addition here. So we set to z. Z is x plus y, so that's z is something plus 1 times 10 to the 12, and then we assert that z is not equal to y. So any guesses of whether or not this assert succeeds or fails? Yeah, it fails. And so an example value that this would fail for is, say, 2. And the reason this fails is because of the limited precision of floating point numbers. So this 1 times 10 to the 12, that written sort of in a binary notation is sort of 1 point. You don't need to know what this is, but the exponent is 2 to the 39. And then say if x was 2, that's 1 times 10 to the 2, which is the same as 1 times 2 to the minus 38 times 2 to the 39. So when the hardware does the addition, what it has to do is take the 2 numbers and make the exponents match. So when it does that, the significand becomes this, and this is a really tiny number. This number is so small that it actually can't be represented as a float, because floats only have 24 bits of precision, and here you would need 39 bits of precision here to make that work. So effectively this here becomes 0, so when you do the addition, it's as if you added 0 to 1 times 10 to the 12. Which is really unintuitive. If you just look at the program, it's not what you would expect to happen, but it's what happens. One other example. So the standard also allows you to set the rounding direction. So when you do a computation, if the result cannot be represented exactly, you can pick which direction it'll round in. So round up, round down, or round to nearest. So in this small example, we have f, which is 0. We set the rounding amount to down. We add 0.1 to f, and then we change the rounding mode to up, and then we add it again, and then we assert that f3 is bigger than f2. So any guesses as to what will happen here? So will this assert pass or fail? No, it passes. It's a little bit subtle. The reason the reason you can get a difference here is because if you notice, there's no f in front of this, which means this is a double constant, not a float constant. So when you do this addition here, you implicitly convert to double, so you get more precision, and then you immediately drop back down again once you assign it to f. And because the rounding modes are different, it allows you to have slightly different values for f2 and f3. But even more interesting is that if you tell the compiler to optimize this, then it fails. The reason it does this is because it decides, oh, I can do constant folding, because we have 0 here, I'm doing 0 plus 0.1, I'm also doing 0 plus 0.1 here. They must all be the same. So it completely ignores the fact that the rounding modes are set here and just constant folds away, and then f3 and f2 become the same thing. Just as a note, this is a bug, but this compiler bug was filed years ago and no one's done anything to fix it. Which is a bit unfortunate, but there you go. GCC and Clang. So GCC doesn't warn. Pardon? Yeah. So GCC doesn't say anything about this. So GCC just compiles your code and then this that fails. Clang is slightly nicer in that it would actually emit a warning. It says, "Oh, you're using this pragma," which is like a hint to the compiler that you're going to be using the rounding mode. But it says, "I don't support this. I don't know what's going to happen." Neither is that good, but Clang is slightly nicer. Right, so anyway, hopefully I've convinced you enough that floating point can be a real pain to work with and really hard to reason about. So I'd argue that it'd be very useful to have tools to actually help developers write programs that use floating point and to help them not make mistakes like this. So there are different techniques we could use: static analysis, some sort of runtime analysis, fuzzing, which is just throwing random input at a program and hoping to see what happens. I'm going to talk about a technique called symbolic execution, which is more heavyweight than these techniques. And by that I mean it takes longer to actually do the analysis, but it's a lot more powerful than some of the others. So just in case you've never seen symbolic execution before, what is it? I'm going to illustrate this with just a small example. So here's another C program, and what we have up here is it says float x equals symbolic, and what that means is what we're going to try and do is execute this program not knowing what x actually is. So it's a symbol. It's not a value that we actually know. So let's see what it looks like to try and execute the program this way. So you start off with the program in this state. So x, we don't know what it is. And inside these brackets, these are the set of current constraints. It's empty at the moment, but you'll see what the constraints become as we execute further. So if we execute the next line, we get to is x less than or equal to 4. And because x is symbolic, we don't know which branch we're going to take, so we just have to consider them both. So if we took the true branch, we'd have now the constraint that x is less than or equal to 4. And we can actually check if this branch is feasible by using a constraint solver. So we can ask the constraint solver, given that x is some unknown number and we know that x is less than or equal to 4, is this satisfiable? And it turns out the answer is yes. So we can carry on going. So we then hit the return statement and the program would exit. And then we can ask the constraint solver for a satisfying assignment. So it might say, oh, x can be 4. And in effect, this satisfying assignment is a test case, because if you replayed this program and replaced the x equals symbolic with x equals 4, you'd follow the same path that we just followed now. So let's try and consider the other path. So we also have the false branch. So not going in here, but just carrying on. So on that branch, we'd have the constraint not that x is less than or equal to 4. We can ask the constraints over again, is that satisfiable? It would say yes, so we can carry on. So then we get to this else if statement. And again, if we want to consider going into here, we have to add a new constraint. So it's the constraint we had before, but now we're saying and x is greater than 4. Again, we can ask the constraint solver, is this satisfiable? And it is. And so we hit the return 1 statement and we'd exit, and it might generate a value like x is 10, for example. And now there's one branch left to visit, which is the false branch. And that the constraint for that will be it's not x less than or equal to 4 and not x greater than 4. Now it looks like that wouldn't be satisfiable, but it actually is. And the value that would satisfy that is nan, because nan is false in almost every comparison. So hopefully this sort of illustrates to you sort of what symbolic execution does. It's effectively enumerated every single feasible path in the program and generated a test case for each path. Okay, so now onto the work that we've done. So we've taken a tool called Liew, which is a reasonably well-known symbolic execution engine, and basically taught it how to execute floating point programs. So yeah, Liew is open source, and you can find it here on GitHub. So it's a symbolic execution engine for C programs. It's built on top of the LLVM compiler infrastructure, so which is kind of a blessing and a curse. So it's kind of nice because we work with the internal compiler representation, which means we see the compiler optimization, so we know what it's trying to do. But other times that can sometimes that can get in the way, but sometimes it can help us find bugs. And it supports multiple solvers for reasoning. So there are some solvers called, say, SDP, Z3 from Microsoft, and Meta SMT. So yeah, adding floating point support to Liew, what do we do? So what Liew does, so the open source version of Liew, what it does normally is if it sees any symbolic floating point data, it concretizes that. And what I mean by that is it just asks the solver, just give me some bytes for this value, because I don't know how to reason about constraints over floating point values, which is okay, but it means we can miss bugs. So we extended Liews expression language to model floating point constraints, and we use the Z3 solver, which supports a theory called called floating point, which is defined by an organization called SMT-lib, to solve constraints. This theory has IEEE 754 semantics, which is great because that's what we want to model. There is another solver that can also reason about these constraints called MATSAP5, but we didn't use it because Z3 is already integrated into Liew, so it made sense just to take the easier route. So, onto a bit of friendly competition. So, at Imperial College, we sort of forked Liew, made our own copy, and added floating point support. And roughly about the same time, we discovered that RWTHR basically did the same thing. But by the time we communicated, it turned out to be a bit too late to work on the same implementation because they had pretty much finished theirs and we had pretty much finished ours. So effectively, we realized, oh, we have two mostly independent implementations. Why don't we try and compare them with each other? So what we did is each team created a set of benchmarks that they knew their tool would work on. Then we basically exchanged benchmarks, and inevitably, doing the exchange of benchmarks means we found bugs in each other's tools. So we allowed time to basically fix and optimize our tools with respect to the entire set of benchmarks, and then we exchanged the actual tool source code and then actually did a comparison. So what were the benchmarks, you might be wondering? So each team basically wrote 28 synthetic benchmarks and sort of 15 semi-real-world benchmarks. So each benchmark came with a specification. Basically said, is the benchmark correct, is it incorrect? And if it was incorrect, where the expected bugs were. So having a specification was really handy because it meant we could unambiguously communicate with the other team as to whether each benchmark was expected to be correct or incorrect. And also we could actually make this automatic as well, so we could just run the tools and check if, say if the tool said, oh, there's a bug, we can just look at the spec and see if we expect to find it here. So what do the synthetic benchmarks look like? We had 32 that we expected to be correct, 24 incorrect. And these are just sort of small test programs. They were sort of written to test particular IEEE 754 features, sort of, and particular edge cases. We also included a copy of William Kahn's Paranoia, just for fun. I don't know if you've ever heard that benchmark, but it's quite a famous one. And also, for these benchmarks, most of the actual input into the benchmark is symbolic, other than the benchmarks that are supposed to be all concrete. So William Kahn's Paranoia is completely concrete. It just tests a bunch of floating point arithmetic to make sure that the results are correct. I'll skip that, doesn't matter. So onto the real world benchmarks. We had roughly about 20 correct, 10 incorrect. And these are, the way these are written is there's a small test driver that then exercises real world code. So, for example, the GNU Multiple Precision Library and the GNU Scientific Library. So, for scalability reasons, the input to these programs is partially symbolic. Okay. Yeah. And also, the location where bugs are is actually in the driver itself. So we didn't put any bugs into these libraries. We just the driver, sort of the driver code, which is just the code that is trying to use the library. We injected bugs into that portion of the code. So onto the evaluation. So this is work in progress. So a lot of numbers are currently missing, unfortunately, at the moment. But I'll try and show what we sort of have at the moment. So what we observed when we exchanged the benchmarks, unsurprisingly, is that none of us quite got the benchmarks right the first time. Both teams sort of forgot about nans in some cases, so which were, it only sort of became, these problems only became apparent when we sort of ran our tools on the benchmarks for a sort of a much longer period of time than we had done sort of just playing around on a machine. So we'd run it on a cluster, say, for an hour and see what would happen. And yeah, we found a whole bunch of problems related to nans. There were a few benchmarks that didn't even terminate, which was a bit unexpected. So our tools found certain inputs which caused a loop to go forever. There was also, this is a real edge case, but there is also this type called a long double, which you can use from C. And there are particular values of that caused us problems. You can ask about that later if you like. And also, one of the benchmarks had problems with the atof function. So atof is a C function that you give it a C string and it spits out a double number. The person who wrote the benchmark wrote it assuming that atof would only ever be given sort of decimal syntax, but they forgot about scientific notation, so one of the benchmarks failed because they didn't take that into account. So now on to how similar our implementations were. So here are some of the things that were very similar. So both teams extended the constraint language in a very similar way. Okay. Both used Z3 for solving floating point constraints. One feature that we neither handled was something called exceptions and flags. So this is something that's part of the standard, but we decided that it would be quite expensive to try and handle this in a sound way, so we just skipped it. But both teams handled setting and reading the rounding mode. It's also a little bit tricky that NAM actually has multiple binary representations, and this is something that neither team quite got right. Onto differences between the implementations. As I mentioned, handling this type of long double was a little bit tricky. So on x86, this is an 80-bit float, which is not it's not a binary format that's specified by IEEE 754, which means we can't model it directly in Z3, but we can indirectly model it, and both teams did that, but we did it in slightly different ways, and our way, Imperial's way, was technically slightly worse, so we ignored certain edge cases just to make our implementation simpler. Math library functions are also a little bit of a problem. So what we at Imperial did is we would just interpret a math library function every time it's called. So say something like square root, we would just execute the C library implementation. But that can lead to sort of lots of paths being considered. And a way of avoiding this is to just model that function as a constraint. So don't interpret square root, just make it part of your constraint language. So yeah, when we exchanged benchmarks with Arkham, we discovered that some of their benchmarks worked incredibly badly in our tool, so we replaced fabs and square root with a constraint language version. We also had a heuristic to work around some deficiencies in how Z3 handles the queries, the constraints we give it. And we also had a heuristic to working around the bug in CLI itself. So as I said, we're a little bit sparse in numbers at the moment because we're still rerunning experiments, but this chart here just shows sort of what the overlap of the tools is like. So this is showing for the benchmark that we expect to be correct, how the tools perform. So 34 benchmarks, both tools could perform. Arkham did 1, Imperial did 3, and there were 14 benchmarks that neither tool could handle. And this is simply just either to the tool timing out or crashing. And it's quite similar for the number of bugs found too. So onto scalability. Unfortunately, this doesn't scale too well at the moment because the constraint solver is the bottleneck. And the solvers need to be optimized to our use case. At the moment, they're not. Other things we could also try is actually doing the constraint solving in a different way. So we could try some sort of heuristic-based search. So just to summarize, we've implemented 2 different versions of CLI that handle floating point constraints. We're currently in the middle of empirically evaluating them. The benchmark suite is also open source. You ask me for the link later if you want it. And the 2 separate implementations are going to inform another implementation that we're actually going to contribute to open source. So we're going to take ideas from both and combine that to make an open source contribution to CLI. Also, the queries, the constraints we gathered, we're going to donate to SMT Comp, which is a competition for constraint solvers, because most of the solvers don't seem to be well optimized to our use case, so we want to change that. So that is all. So thanks for listening, and any questions?
So I have a question. Do any of your, well, I'm imagining like a really difficult case to check. So let's say you're working with arrays of floats, and you want to say something at the end like, there's conservation of energy in this process, so the sum of all of the floats in this array is preserved at the end. Can you deal with things like that?
You, as the programmer, have to write that. So I mean, we're just interpreting a C program, so you have to write an assertion that is equivalent to checking the conservation of energy. But it's like tricky part there is you're writing the check also in C. So
Right.
the way you write your check could be wrong as well, because you could get the addition wrong in some way.
But let's say I can get it right.
If you can get it right, then it will check the assertion
Yeah.
for you, and if it's possible for it to fail, it will tell you it will fail.
And do you have any idea of how long it would take to symbolically sort of check that? Let's say it was a arrays of 1,000 floats or something.
That would take a long time. I mean,
Like a day or?
Well, we didn't even try with that much symbolic data. We did a few examples of matrix multiplication, but we found we had to make only it partially symbolic in order to sort of generate a few interesting test cases, because the solvers really are just not fast enough at the moment. So, I mean, the way they're implemented internally is you take it takes the constraints and then sort of bit blast that, so it converts it into a model, basically a model for every single hardware unit. So every time you use a multiply, you're suddenly creating this huge circuit, and then that converts it to stat, and then it tries to solve that. And if you have lots of multiplies and divisions, it's soon really, really struggles.
So a question, might be a bit off topic, but have you studied uncertainty quantification bounds just on floating points? So if I code something to calculate the first order differential or function or something, and you do some analysis and you give it the bounds where this should be in, and obviously if it's within the bounds, then you know it's fine, and if it's outside the bounds, then you know there's a bug in the implementation. Have you looked at something?
No, we haven't done that. frankly, I don't have the expertise to be able to write that sort of assertion, because you need to be good at doing bit bounds analysis, which is not something I've ever learned how to do. But if you know how to do it, then yes, you could do it. Provided you could write the assertion in C saying assert some condition. Provided you can write that, then this tool will check it. But you need the domain-specific knowledge of actually how to write the bounds, which I don't have. But if you know how to do it, then yes, you can do that.
I think we'll do the rest of the questions offline so we can have a bit of a break. So let's thank our speaker again.
Thank you.